Cardinality is a simple idea, but it's also a very powerful tool. The cardinality of a set is just the number of items in the set. And when we talk about cardinality of data sets, we're really talking about how many distinct values are there in a data set. And the cardinality of a data set might be small relative to the size of the overall data set. Like, let's say we have a bunch of data records that talk about voters registered in some district, and one of the fields is the age of the voter, just how many years old is the voter. Well, there might be a lot of voters, but they're probably only going to fall into 70 or 80 or so distinct bins in terms of what their age is. So that's an example where the cardinality would be small relative to the data size. However, if our data set was their names as opposed to their ages, well, there's more distinct names, obviously. That might be a larger cardinality data set. Or, imagine we could go even more in depth, their age, including their date of birth and their name. Now we're talking about very high cardinality. So let's just think about the idea of cardinality and how we would calculate it for a data set. What we'll eventually use this for is we're going to use cardinality to talk about not just how many distinct items are in a data set, but how similar are data sets, right? So you can imagine if we can do cardinality on a data set and we could extend that somehow to do cardinalities on unions and intersections of data sets, we're starting to talk about similarities. That's where we're headed. Okay, so let's just picture a data stream. Imagine that what I have here is just one small piece of a larger data stream. Maybe there's a lot more values up here and a lot more values down there, but I've just excerpted it. And over this whole data stream, we want to ask the cardinality question. We want to ask how many distinct values are there in that data stream. Okay, so algorithmically, what's a strategy for how we could solve this problem? Let's start simple. So a very simple strategy would be one where it would probably follow the pattern of what you would do visually if you were trying to solve this problem just for the numbers currently on the screen, right? Like, I tell you what I probably would do if I was trying to solve the problem right now, looking at this slide. I would sort of pick one of them, like maybe 946 here, and then I would just visually scan the rest of the items looking for any other 946s. And I wouldn't find any. So I'd say, okay, 946 seems to be distinct, right? So I would increment, a counter for 946. Okay, so then I'd move on. Maybe I'd do 5581. And then I would scan and say, okay, do I see any other 5581s? And so on. And if we encounter an item that actually does exist elsewhere in the data set, then we know we should only count that item once. So maybe we only count it the first time we see it. So this kind of strategy where we pick a particular value and then scan to see whether that value occurs more than once so that we can do the correct bookkeeping to count the number of distinct items, I'll just call that quadratic scan. Right, I call it quadratic scan because it's like if the length of the data stream is m, then this process is a m squared order strategy, right? We're sort of, first of all, we have m different choices for what we could pick as being the value that we're going to concentrate on. And then to figure out whether that value is repeated, we have to scan potentially most of the vector, most of the data set to figure out if it occurs more than once. This is why I call it quadratic scan. What about space, right? So I haven't said how we're supposed to account for the size of the data set. Like, is the data set flying by at warp speed and we can't possibly store it? We just have to do something as quick as we can on one data item at a time? Or are we actually storing it so that we can do this analysis? Well, it's kind of not a real question for this strategy. For this strategy, we really do need to store it because we need to be able to scan forward and backward. We need to be able to pick the value that we're interested in and then scan all the way down to the bottom of that data set at any given moment. And we're doing it again and again and again. So there's really no question. We need to have this data set stored in order to be able to scan forward and backward repeatedly. Okay, so we need big O of m squared time for that scan, and we need big O of m space to store the items so that we can conduct the scan. Okay, so that's one idea. Quadratic scan is one idea. What's another idea? You know, as long as we are okay with storing the entire data set, it seems like another door has opened, which is maybe we can just take the whole data set and sort it first. And why is this appealing? Well, because it seems like by sorting first, we may be able to attack the big O of m squared, because after all, we can use one of our favorite sort algorithms, you know, merge sort, for example, to achieve m log n time, right? Assuming that we can compare two of the items in this list in constant time, which when they're numbers is a reasonable thing to assume, then we might be able to get away with at least, you know, if we do this first, if we do the sorting first, and then we can come up with a clever way of finding the number of distinct items given a sorted list, we have a shot at perhaps doing better than big O of m squared. And indeed, it's pretty easy to see how we would do this. So let's say we did sort the list first. Then what would our strategy be for counting the number of distinct items? Well, now it's as simple as scanning the sorted data set from top to bottom. And every time the value changes, we know that we need to increment the number of distinct items seen so far. If the value doesn't change, you know, if we see 7 and then we see 7 again, we know that once we've seen that second 7 or maybe a third 7 or a fourth 7, we don't need to increment because we've already seen 7. So we just basically need to count the number of times the value changes, and that tells us the number of distinct items in the data set. So that's just a linear scan that we need to conduct once we have actually sorted the data set. So we need m log m time for that sort, and just order m time for the scan. And the amount of space that we need, we can probably keep it down to big O of m. In other words, we could just store the data set itself, and then we could use a sorting strategy that uses a small amount of additional space or no additional space. Maybe it's totally swap. We'll just use swapping operations, for example, to put it into order. Okay, so those are two fine ideas, this quadratic scan and then a sort followed by a linear scan. Here's a third idea that's a little wackier, but it might actually make sense in some circumstances. So here I'm not going to do anything to the data stream. The data stream can be flying by at warp speed, as far as I'm concerned. But the way that I'm going to account for how many distinct items I've seen is I'm literally going to store an enormous bit vector with one entry for every possible item in the universe. Okay, the universe from which the items of the data stream are drawn. So for example, if the data stream consists of numbers, let's say 32-bit numbers, then I have a 2 to the 32 sized universe. You know, any given value might be any of the 2 to the 32 choices. So if I wanted to keep track for each of those 2 to the 32 possibilities, whether I've seen it yet or not, as the data set flies by, I could simply allocate a bit vector with 2 to the 32 entries, initialize everything to 0, and every time I see a value, I do a direct address lookup into that bit vector, maybe with a little bit of fancy bit operations to get at a particular bit that corresponds to our item. And I just check to see if it's 0. If so, this is the first time I've seen it. I'm going to switch it to 1, and I'm going to increment a counter for how many distinct items I have. Okay, so here the stream can be going by as fast as you like. We just need for each item in the stream to be able to, just enough time to be able to go do a direct address lookup in the bit vector and possibly set that value to 1. So how much space do we need? We need as many bits as there are possible items in the universe. So we could call this big O of size of big U bits of space. Depending on the size of the universe, that can be, of course, be completely impractical, right? The universe might even be of unbounded size, like we're dealing with strings of arbitrary length or something like this. But it's a strategy we could imagine using. And it works well if the stream is passing by quickly. So what's one more strategy? Well, I've left out kind of an obvious one and a very practical one, which is to use a hash table. right? If we can use a hash table, then we can simply, again, as the data set's coming through, each time we see a new item, we go to try to add it to the hash table, and if it's already there, then we don't add it to the hash table, right? In other words, this hash table is really just representing the set abstract data type, so it's kind of like a hash set. And so we'll try to add the item. If it's already there, we give up, and we do that for each item as it comes in. Okay, so again, this is applicable to a stream that might be moving by very quickly. Right, we're going to do some sort of constant time lookup and maybe amortized constant time insertion or something like that for this hash table. But the key is that at the end of the day, how large can this hash table possibly grow? Well, it grows to exactly the cardinality of the data set, right? Because we are simply taking the data set, which might have repeated items, and creating a set data structure for it, which does not have repeated items. And it never grows larger than that. It just slowly grows to be that size. And so we can upper bound it by saying that the space required is big O of the number of distinct items in the data stream. All right, and I'll use this like somewhat cumbersome notation to refer to the number of distinct items in the data stream. So this obviously will work. I guess the trick is that even the number of distinct items in the data stream could be very large, right? So it might very well be practical from a time perspective to do this with every item coming by as the data stream flies by. But eventually, depending on how large the number of distinct items in the set is, how large the cardinality is, we might end up with a really, really big hash set. Okay. And of course, if we can use a hash set, we've already, in other videos, seen a data structure that we could possibly use to approximately represent that set, which is a Bloom filter, right? So this is another option available to us. Fairly practical option, actually, which is to use a Bloom filter, live with the fact that we're going to have some collisions, and therefore we're only going to be able to approximate the cardinality of the input. Maybe that's fine. In fact, we will mostly just be approximating the cardinality of the data set here. And how would we actually come up with that cardinality? Well, we would populate our Bloom filter. You know, each item coming in, we would add it to the Bloom filter. And then at the end, we now have a populated Bloom filter. It's got some set bits. It's got some unset bits. We would simply take the fraction, let's say we would take the fraction of unset bits. Okay, and that would be, thinking back to the Bloom filter lectures, that would be the thing that we called tilde p sub 0. We could just plug it into one of those equations and solve for m, and that would give us the cardinality of the data set, an estimate of the cardinality of the data set, taking collisions into account in the process. Okay, so these are all ideas for how we can do it that are to varying degrees practical. But when the data set is very, very, very large, none of these ideas are practical. So what we would like to work toward is an approach that lets us estimate the cardinality of a data set that's extremely practical, where we have a high degree of control over how large the data structure we're going to produce is, right? When we use a hash table, we don't have any control. It's up to the cardinality, right? And we don't know the cardinality to begin with, right? So we're not really able to control the size of the data set. But what if we could fix the size of the data set at the outset? Say, okay, our data structure that we're going to compile that's going to allow us to estimate the cardinality can only be this many bytes. All right, that's the kind of strategy we eventually want to use. Okay, so later we'll come back to the question of how we can use cardinality to do useful, practical things like compare how similar two data sets are. Let's just start now with this idea of a very, very small amount, a very, very small data structure from which we can estimate the cardinality of the data set. Okay? In fact, we're going to get it all the way down to just one number, right? So it's going to be incredibly small. And then we'll work back toward, well, okay, we want a better estimate. Maybe we need to make it larger, and then we'll be able to talk about how to use it for similarity. Okay, so let's start simple. Let's say I have the following scenario. I have a deck of cards, but it's kind of a special deck of cards. They're not playing cards. They're just cards labeled 1 to 1,000. So I have one card for each number for the integers labeled 1 to 1,000. I'm going to take some random subset of those cards, right? Could be large, could be small. I'm going to take some random subset of those cards and put them in a hat where you can't see them. And what you need to be able to do, you haven't peeked at the cards and you can't peek inside the hat, but your job is to estimate n, the number of cards in my subset. The number of cards in the subset that I put in the hat. And you can get some information from me. Specifically, you can ask for one representative card from all the cards that are in the hat. Okay, I should say some more about what it means to pick this representative. How would you pick it? Well, let's say your choices are, you can pick a quantile, by which I mean you could pick like the median, or the minimum, or the maximum, or the 25th percentile, or something like that. You can say, show me the median of all the cards in your hat, or show me the minimum of all the cards in your hat. Will this help? Will this help us estimate how many cards are in the hat? It seems like not a lot of information to only get one value from among the cards in the hat. But let's think about that a little bit. Let's say we pick the minimum. So, in other words, your strategy is you'll ask me for what's the minimum among the cards in the hat. And let's just think through, what would it tell us if the minimum, remember the cards are labeled 1 to 1,000. So what would it tell you if the minimum was 500? Would you think that the number of cards in the hat was large or small? You should think that the number of cards in the hat is small, maybe quite small, like maybe 1. Maybe there's just 1 card. If the minimum is that high, because if there were a large number of cards in the hat, then the idea that all those cards would be 500 or larger, that would be a huge coincidence. You know, that would be like flipping a coin and getting heads every time, right? So, in other words, it's unlikely that I have a large number of cards. But if I just had 1 card, sure, that card might very well be 500, right? That card is equally likely to be any of the 1,000. Right? So seeing a high value as the minimum is a hint that the set is probably not that big. Okay, what if the minimum was 10? Okay, now that's smaller, right? So now we wouldn't estimate such a small size for the set in the hat, right? Obviously, there could still just be 1 card in the hat, but it's starting to look like more likely that there are many cards in the hat. And then likewise, what if the minimum was 4? What if the minimum was getting smaller and smaller? Our estimate for the cardinality would get bigger. Okay. So we can visualize this, right? So since we picked this particular scenario where we have cards labeled 1 to 1,000, I can just picture the domain from which those cards are drawn like this. I'll just subtract 1 for math purposes, so I have them labeled 0 to 999 here. And let's pick a scenario where, let's say, you asked for the minimum card, and I showed you the minimum card, and it was 95. All right, so we went sort of this far along the domain to get to the minimum. So this actually does give us a strategy for estimating how many cards are in the hat. Let's just say for a moment that without any other information about what cards are in this subset, remember it's a randomly chosen subset, without any more information about what the randomly chosen subset is, we might reasonably assume that the cards in that subset are just scattered across this line, randomly, roughly uniformly, let's say. You know, in the absence of any more information, we could just say, oh, well, they're kind of, maybe they're uniformly spread out, along this line. And so, if we have n cards, capital N cards, they're going to split this line. They're going to essentially partition this line into how many pieces? N plus 1 pieces, right? So in other words, if, like, just as a very simple example, let's say the set really is just this and another value up here, like 800 or something like that. So here N is 2, capital N is 2. I only have 2 cards, but they divided the domain up into 3 pieces, right? This piece, and then this piece, and then this piece. Okay, so let's just informally say that if we have n points and they're just scattered randomly across this interval, it divides the interval into n plus 1 parts. And each of those parts, without any better information, we could say are equally, have equal size in expectation. So we expect them to be about 1,000, which is how many cards there are, divided by big N plus 1 long. Okay, well then now we can write down a guess as to what's the cardinality based just on the fact that the minimum is 95. So, because what we can say is, okay, the 95 is just the length of one of these partitions. So 95 is about the length of one of these partitions, 1,000 divided by n plus 1. And I can just solve for n. All right, so let me multiply by n plus 1 and then also divide by 95. I'll get this. Oops. 1,000 divided by 95, which is 10.5. Okay, so I've got n plus 1 is about equal to 10.5. Therefore, I can say n is about equal to 9.5. Then there you go. I have my estimate for the cardinality, based just on the minimum. Okay? And then another thing I'll observe about the minimum. Remember I said you could pick any quantile. So why pick the minimum? Right, we could have picked the median, and the median would similarly give us some information about the cardinality, right? If the median is very close to the midpoint, that's a good sign that the set is larger. If the median is far from the midpoint, that's a good sign that the set is smaller. Okay, so why would we prefer minimum? Well, when the data stream is flying by at top speed, it's really easy to calculate the minimum. Right? All you really have to do to calculate this sort of cumulative minimum is check each value as it flies by and ask, is it smaller than the minimum so far? And if so, update the minimum so far. If you're looking for the median, you can just think through that that's actually a much more complex question. How do you in a so-called streaming fashion, calculate the median of a data set? It's much harder, and it sort of inevitably is going to involve storing more data. You know, maybe you're storing samples or you're storing some summary of the distribution or something like that. But it's going to be substantially more complex than calculating just the minimum of the data as it's flying by. So it's actually pretty profound that just by storing one number, right, in this example it was this 95, right, that's the only number we used in our calculation besides the number of possible cards, which was 1,000. That was sort of a given. Just with this one number, the minimum of all the items in the data set, I was able to produce an estimate for the cardinality of the data set. One number. And furthermore, that one number was easy to calculate because it's easy to calculate the minimum no matter how large the data set is. So our strategy involves taking the minimum of all the values in the data set, but we can ask the question, right? If often when we're trying to infer something about a population parameter, like how many distinct items are there in this data set. A typical set of techniques we might use are like statistical techniques, like sampling. So how's what we're doing where we're taking the minimum, or I kind of glossed over this, but it's equivalent to take the maximum, minimum, maximum, same thing, as long as we assume that the subset's a random subset, then there's nothing fundamentally different about the interval length that we get by taking the minimum versus the maximum. How does this compare to if we were doing random sampling? Well, actually, random sampling, even though it's kind of the usual way you might think about problems like this, doesn't do anything in this case, right? Like, what does a random sample tell you about the cardinality of the set? The set itself was a randomly chosen subset of cards, 1 to 1,000. So getting one representative from that subset doesn't really tell you anything about the cardinality of the data set. You know, you could imagine a scenario where you sample so many times that now you have the entire data set, but that's absurd, right? We're trying to do it that's obviously going to break the bank. We're trying to do it in a very small amount of space. So random sampling doesn't really get us the information we need here. maybe a kind of biased random sampling could. Like, for example, what if we were doing random sampling, but we were actually trying to get we were trying to favor the smaller values, right? So that we would hopefully get the minimum, or if not the minimum, something close to the minimum. Then maybe use the same sort of approach to turn that into an estimate for the cardinality. Okay, or we're trying to do some biased sampling so that we're not necessarily getting the minimum, but we are trying to get consecutive pairs of items so that we can again try to measure that interval length. In a way, taking the minimum like we're doing is just a really biased form of sampling, right? So there's, in some sense, what we're doing is related to sampling. It's not the same thing, but in some sense it's using bias sampling to our advantage. There's another problem with sampling here because specifically for this problem of trying to get the cardinality, the number of distinct items, the minimum is a nice way to ignore duplicates, right? Because sampling does not generally ignore duplicates. If we were sampling from the input stream, we might sample the same value. There might be one dominant value that appears 99% of the time. If we're doing sampling, we'll probably keep sampling that over and over again a lot. And that's extra not helpful in estimating the cardinality. So the minimum is not vulnerable to that, right? If we are taking the minimum, it doesn't matter whether the input items are repeated or not repeated, whether they're repeated very frequently or not very frequently, in contrast to sampling, where sampling would be thrown off. You know, if you, for example, had one extremely dominant value, but you only took a few samples, you would probably just see that dominant value, and any non-dominant value would be hidden from you. It wouldn't be available to your estimate. Okay, so in a way, again, taking the minimum is like a really, really biased version of sampling. Okay, so let's come back to this question of why do we care about the hat problem again? Because remember, the hat problem seems a bit contrived, right? Because we're talking about taking a random subset of cards labeled 1 to 1,000. Does that really correspond to real-world scenarios? And actually, the answer is if we're using a hash function to hash the input values, then yes, that actually does correspond to the way the output of the hash function is expected to behave. So let's think about this a little again. Let's say this is the range of our hash function. And so our hash function is fulfilling its usual role of randomly spreading the values out along the range of the hash function, you know, sort of plopping them down on random places. And let's do something a little different than what we've typically done, which is to think of the hash function actually not as outputting, let's say, 64-bit values, and then letting that be a slot in an array, like in a hash table or a Bloom filter, or taking it mod some number and then letting that be a slot. But instead, to think of it as mapping to values between 0 and 1. In other words, we'll take the hash function, we'll find some hash value, maybe it's a 64-bit hash value, and then we'll divide by the maximum possible hash value. All right. In the case of a 64-bit hash function, that would just be 2 to the 64 minus 1, assuming it's an unsigned 64-bit number. And so the hash function is essentially randomly picking for every distinct value in the data set a spot between 0 and 1 inclusive. So it might be equal to 0, it might be equal to 1. With very fine resolution, because 2 to the 64 is a big number. So now this is essentially the hat problem, but where the numbers on the cards corresponds to the slots in the range of the hash function. Or now we've turned it into thinking of it more continuously as being between 0 and 1. But because there's randomness in the hash function and it's spreading things out randomly, then we can think of it as like the n cards that are in my hat, right? Though as a random subset of the universe as being what we have. So the randomness in the hash function is what turns any dataset cardinality problem into the hat problem. And this is consistent with what we've seen all along. The randomness in the hash functions is what allows us to take assumptions like uniform spread across the range that don't really apply to the input data, but we can still assume them because they do apply to the output of the hash function.